welcome to Reaction Stoichiometry. In today's lesson, what we're going to be looking at is how molar quantities relate throughout an entire chemical reaction. What can be kind of helpful here is starting by thinking of a reaction you might be a little bit more familiar with, such as baking cookies. So I have a typical recipe up here with some different amounts of the flour, eggs, sugar, and chocolate chips that you would need to do a synthesis reaction and get a dozen cookies out of that. In order to make 2 dozen cookies, so if we wanted to do twice what we have written up there, we would be doubling the amount of flour. So our recipe calls for 2 1/4 cups of flour. We'd be multiplying that by 2, and that would be 4.5 cups of flour. If we wanted to bake 2 dozen cookies, so again, we're doubling that recipe, we would double everything in it. So usually we use 2 eggs, and we would just be multiplying that by 2. And we would use a total of 4 eggs. So if we want to double our product, we just double the amount going in. If we look at this a little bit differently in terms of number of cookies instead of dozens, this can be a little more confusing. So 42 cookies is actually 1.75 dozen cookies. Now, assuming that probably the easiest way to do this is really thinking in terms of making maybe more cookies than that. So instead of making 1.75 dozen and chopping all those numbers, we'll just make 2 dozens, maybe give the extras away. So in this case, in order to make that many cookies, since we have to buy bags of chocolate anyway as a full bag, you can't get part of a bag of chocolate, we would need a total of 2 bags. Sometimes we also think about something called a limiting reagent, which we won't get into much in reagents chemistry, but it's a nice idea to think about. If I have plenty of flour, as much flour as I need, I have a lot of sugar, I have, just oodles of chocolate chips. But if I were limited because I only, for some reason, had 7 eggs in my refrigerator, this would limit the amount of cookies that I made. Each of my dozens requires 2 cookies. I'm sorry, 2 eggs in order to make a dozen cookies. So really here I have enough for 3 1/2 dozen cookies. And again, if you don't want to chop all those numbers, you might actually only end up making 3 dozen cookies, so you don't have to do all that crazy math. So in other words, I'd be making 36 cookies. Or if you're willing to do all that math, you could actually make 42 cookies if you're feeling crazy. I don't like doing all that math with cups and all that stuff, so I personally would avoid that. So let's do some chem with this. I've given you a reaction with some molar quantities in it. Molar quantities are represented by coefficients. So this 2 right here means that in this reaction, we're talking about reacting 2 moles of hydrogen gas. There's an invisible 1 here, indicating 1 mole of oxygen gas. And those quantities would make us 2 moles of water. We can go and do GFM calculations for each of these. So each of the hydrogens is 1.0079. So each of these little individual atoms weighs that much. And because we have the 2 in front and we have that 2 there, we actually have 4 of those. So the number of grams we have is about 4.032 grams of hydrogen going into this reaction as written. We have 2 oxygen atoms. Each one is 15.9994 grams. So we have a total of 31.999 grams of oxygen. And for our waters, each of our oxygens, remember, is still 15.9994. And each of our hydrogens is 1.00794. So we add each of these up. Each of these groups are about 18. We multiply them by 2. So our GFM comes out to be 36.031. The reason I want to make this comparison is so that you can see that what we talked about in our conservation of mass unit still holds true here. If you add 4.032 and 31.999, it's going to come out pretty darn close to 36.031, save for a little bit of rounding error, but it will come out pretty close to a pretty far out decimal place. So you can check that on your calculator. So we can actually solve these using regular conversion factors, doing the things that we were doing before. So we want to know how many moles of oxygen are required to make 2 moles of water. So in this, what we're comparing is O2 and H2O. So there are two potential conversion factors we could make here. There's a 1 in front of O2, so we could say if we put in 1 mole of O2, we get out 2 moles of H2O. We could also say if we put in, or if we want to get out 2 moles of H2O, it's because we put in 1 mole of O2. So these are equivalent conversion factors based on the fact that there's an invisible 1 right here and that 2 right there. So next thing I'm going to do is I'm going to just jump down to my little problem solver down here. My starting amount is going to be my 2 moles of water. So I'm going to write 2 moles, and I am going to write H2O with this. This is going to be really important in keeping track because we have moles of different substances. So because I have moles of water on top, I need to have moles of water right down here on the bottom. So in order to be able to cancel out those moles, I'm going to pick this first conversion factor right here. So my 2 moles of water will be on the bottom, and my 1 mole of O2 will be on the top. What this allows me to do is cancel my moles of water. Now I have moles of O2. So I go back to my problem, and that's exactly what I wanted to know. How many moles of oxygen are required? So I've got my entire setup here. So I'm going to do 2 times 1 divided by 2, and this will give you 1 mole of O2. Sometimes it's nice to actually write that that O2 goes with that. So our next problem, we're going to look at how many moles of oxygen are required to make 1 mole of water. So we're still comparing oxygen with water. This is still based on that same reaction that we were looking at on the other page. So we're still using our same conversion factors here. 1 oxygen gives us 2 waters. So those are still going to be our conversion factors. I'm not going to rewrite those. Our starting amount here is our 1 mole of water. So we're going to plug in 1 mole of H2O. So in order to get, we want to have moles moles of H2O on the bottom. So looking back at my factors here, I'm still going to use the same factor I used before, which is 1 mole of O2 over 2 moles of H2O. I'm then able to cancel out my moles of H2O. 1 times 1 is 1, divided by 2. This will give me 0.5 moles of O2. So these are some pretty straightforward, simple questions. It can get a little bit more complicated once grams are involved. So we're going to jump into a gram question. How many grams of hydrogen are required to make 36 grams of water? Now we are going to have to look back on our equation again here, okay? So I'm going to just pull this back a couple screens. You can flip back to this on your page. We want to be, we're comparing here our hydrogen and our water. So in this particular reaction, we're looking at our 2 moles of hydrogen and our 2 moles of water. So actually our conversion factors here would either be 2 moles of H2 over 2 moles of water, or 2 moles of water over 2 moles of H2. Now, because grams are involved, we're going to have to start with grams. We want to end in grams, but we got to kind of go through moles here. So our starting amount is going to be that 36 grams of water. I'm going to come down here. Remember, I do want to come out, it's nice to note this a lot of the time, I do want to come out with grams of H2O. So the first thing that I need to do is I need to get things into moles, because my reaction only allows me to compare things that are in moles. So I need to get rid of grams. So I'm going to first do a GFM calculation for H2O. GFM of H2O is 18.0152. Now I'll write that right here. Now remember, as a conversion factor, what this actually allows me to do is flip-flop between whether I want grams or moles on the bottom. I want grams on the bottom, so I'm going to do 18.0152 grams on bottom. 1 mole on the top. So, and actually, I'm sorry, I should practice what I preach here, and I'll put water with that. So this is going to allow me to cancel out my grams of water. Now I have moles of water, and I can use one of my conversion factors from the top. This one right here has water on the bottom, so I'm going to do my 2 moles of water on the bottom and 2 moles of H2 on top, which allows me to cancel those out. Now I have moles of H2, but I want grams of H2. So now I'm just going to simply do another GFM calculation. My GFM for H2, remember you do have to multiply that by 2. I'm going to have my grams on top because I want my 1 mole of H2 on the bottom. That allows me, sorry, I'll write my H2 with that. It really does help keep track of stuff. That allows me to cancel out my moles. Now, mathematically, what you're doing, you got a lot to punch in. It's going to end up being 36 times 1 times 2 times 2.01588. And you're dividing that by 18 times 2. And what you should ultimately get is 14.0 grams of H2. I'm limited to 2 sig figs because that's what I got going on right here. So a couple of problems for you to try. Go ahead, pause the video, and I'll put the work up in just a moment. So for the first one, you should have gotten 8.1 grams. For the second one, you should have gotten 47.9 grams. So I'll show you the work for each of these. The first one, we're starting with 72 grams of H2O. In order to get rid of grams of H2O, we're using our GFM on the bottom. Put us into moles of H2O. This has now allowed us to get rid of our grams of H2O. Now I need moles of H2O on the bottom, so I'm comparing H2O with hydrogen. So that's a 2 to 2 ratio. So I'm going to have 2 moles of H2 on the bottom. Those moles of H2 will be able to cancel. I'm sorry, H2O on the bottom. And then my 2 moles of H2 go on top. In order to change H2 into grams, I'm going to do 1 mole of H2 with its GFM of 2.01588 grams on the top. Once you do the math for this, these are going to cancel, and you should have gotten 8.1 grams. If you did not get 47.9 for the second one, here's your work for that one. We're starting with 54.0 grams of H2O. First, we got to put that into moles, a little GFM action. This has now gotten rid of my grams of H2O for me. Our next conversion factor, we got to get rid of moles of H2O. So I want to compare O2 and water. So I'm comparing this guy right here and this guy right here. So this is a 1 to 2 ratio. So my moles of water, I have a 2 in front of water in the reaction. So 2 moles of H2O will go here. And I have a 1 in front of O2, so that's going to go here. So H2O is going away. Now I've got O2 in moles. I need it in grams. So 1 mole of O2 is going to go on the bottom. And my GFM for O2, which is 31.9988 grams of O2, will go on top. Moles of O2 will cancel. And as you do your math, multiplying across the top and dividing by 18 times 2 on the bottom, you should get 47.9 grams. 3 sig figs, because this number right here has 3 sig figs. Now, I give you one more reaction. What I would like you to do on each of these is not so much stress the sig figs. So I'm not so much worried here about sig figs as I am with you about kind of setting up these calculations and getting more comfortable with with a different reaction. So we've got some more complicated numbers here. I'll show you the answer to this one first. Again, I'm not super worried about sig figs on any of these. So the first one, you should have gotten 12 moles of ammonia. You're starting with, we're comparing moles of ammonia with our moles of water. So this is ammonia right here, and this is water. So our starting amount is 18 moles of water. That's what's given to us in the problem. I want to be able to get rid of my moles of water here. So I have to put moles of water on the bottom. So I go up to my reaction, and I have a 6 in front of water. So 6 moles of water will go right there. I have a 4 in front of NH3. So what this allowed me to do is cancel out my moles of water. I'm now in moles of ammonia, which is what I wanted. So you're doing 18 times 4 divided by 6, and that should give you 12. Another fairly straightforward one like this, how many moles of NH3 are needed to completely react with 12.5 moles of O2? So we're starting with 12.5 moles of O2. We got to compare O2 with ammonia, which is NH3. So I'm going to put my 5 moles of O2 in the bottom and my 4 moles of NH3 on top. So fairly straightforward question again. Your moles cancel out there. 12 times 4 divided by 5 should have given you 10 moles. Again, not worried about sig figs. There are technically 3 really, but not a big deal in this problem. Next we're going to, oh, this is still a mole one, sorry. So we got one more mole one here. The answer you should have gotten for this one, take a minute, calculate it. You got 21 moles of H2O. So you get 21 moles of H2O here. Our starting amount is 14 moles of NH3. Our number that goes with NH3 for moles is 4 in the reaction. So we got 4 moles of NH3 on the bottom. And then we actually want to compare this with H2O. The reacts completely with oxygen, or completely reacts with oxygen, just means we have plenty of oxygen. So we're not actually concerned with that in this problem. So in front of water we have a 6. So we're going to do 6 moles of H2O. Cancel our moles of NH3. 14 times 6 divided by 4 should give you 21 moles. Try the next 2 gram ones. Just pause the video for a minute, check them out. I'll put up work in just a moment. So for D, you should have gotten 270, and E, you should have gotten 40. So I'll put up the work for each of these really quickly. We had 170 grams of NH3, 1 mole of NH3, 17.0, blah, blah, blah. Sorry, that's your GFM for NH3. That puts me into moles. Now I'm going to go up to my equation. I need moles of NH3 on the bottom. So there's a 4. And then I need to convert this. I want to compare it to water. So I've got a 6 in front of H2O in the reaction. So 6 moles of H2O. Let's check where I'm at. Grams of NH3 are gone. Moles of NH3 are gone. I'm in grams of H2O. I need to turn this into moles, and I'm going to do this using my GFM. 1 mole of H2O on the bottom to cancel that, and 18.01528 grams on top, so my moles will go away. And as you multiply across the top and divide across the bottom, that should give you 270. And last but not least, we started with our 30 grams of NO. We need to first turn this into moles of NO using our GFM. reaction. So in this reaction, we want to compare oxygen to nitrogen monoxide. So we want to put nitrogen monoxide in the bottom. So there's a 4 in front of that in the reaction. So 4 moles of NO. And we're going to compare that to oxygen, which has a 5 in front of it. 5 moles of O2. And from here, we can kind of check where we're at. Grams of NO have canceled. Moles of NO have canceled. 1 mole of O2 has a mass of 31.9988 grams. That's our GFM. And when you do the math from that, you should get 40 grams.